Okay, so let's look at solutions for 8.1. And I agree, these are things you have to get used to a little bit too, and so I'm not saying that you expecting you to be able to do all the problems, and we will spend time on fixing and finding these things, and eventually I'm sure you would be able to solve problems like this. So the first one was we're drawing lines. A line, of course, is an infinite line in the plane, and we always draw lines that they can never be, whenever we draw a new line, it cannot be parallel to any of the old lines, and it cannot go to any of the intersection points. Okay, so, and then the question is, so Rn is the number of regions cut out by n lines in this, by n lines that are not parallel and do not, any three don't go into through the same point. So let's not add this here. Okay, and so the question is what given recurrence relation for that? That was 21a, and then 21b is solve this, but let's do this first, the R1. So first of all, we could perhaps say, what is R1? Okay, we have the plane, we draw a line, we have two sections, right? Two regions, so R1 is 2. Okay, so now to understand what goes on, let's try to look at let's draw, let's say that we have already drawn 3 lines. So let's count how many we have here. 1, 2, 3, 4, 5, 6, 7. Okay. And now I'm going to draw one more new line and see how many more regions do I get. Okay. So here's my line. It has to go, it cannot be parallel. That means it has to intersect any of the lines that I have so far. So at this point, n is 3, right? So now I'm going to go to n is 4. And so it has to intersect every point, every line, because none can be parallel. And the line that I'm drawing can also not go to any of these points. So we get a new intersection point with all 3 lines that I have so far. So here's, for instance, my 4th line. Okay, let's see what happens. Let's start from the left, so to speak. Well, from the left, you see that region 5 has been split in 2 regions, right? Let's call it 5 prime and 5 double prime. Okay? Now, at this point, I'm crossing the line here, and when I cross the line, I enter a new region, in this case, region 6, and what I do, I split that region in 2 parts. This is 6 prime, and this is 6 double prime. Okay? Then, the next time I cross the line, I enter a new region, correct? And so what we see here is that region, that new region 7, is now cut in 2 parts, namely 7 prime and 7 double prime. Finally, I'm cutting this guy, right, the last of my lines, and I enter a new region. In this case, it's region 3, and so this region is split in 2 regions, 3 prime and 3 double prime. Okay, so let's think about it. Each time we cross a line, we enter a new region that we then split in 2. So how many regions have been split in 2? In this case, you see 1, 2, 3, 4. Why 4? Where does this number come from? Well, we have 3 intersection points, so 3 times we enter a new region, but of course we started in a region. We started in a region and then we entered 3 new regions. So 3 plus 1 is 4, that is n. Okay, and so now we can, from doing, that's often what you need to do, is to understand these things on small examples and see how this works. Now, of course, I'm presenting it to you as a solution. It's much harder to actually find it. You have to play with it, you try out, you might try different recurrence relations. Perhaps some of you thought, okay, each time I draw a new line, every region is split in 2. And then if you think that is true, then you should check that. So whatever you think, oh, this might be the formula, that's the formula, check it on easy examples. Okay? And you see, this is not the case, right? Notice that these regions here, 1, 2, 4, and 3 have not been, 1, 2, and 4 have not been split in 2. So it's not true that every region is split in 2. It's only n regions that are split in 2. So in the more general case, we can now say that if we would have all these lines here, I'm not going to draw all of them anymore, and I draw my new purple line, that is now the end line. This is going to intersect all these lines. Okay. We start with this region that has been split in 2. Then we enter a new region that will be split in 2. We enter a new region, that's very briefly, but we split it, we split it, we split it, and we split it. And how many times does this happen? This will happen n minus 1 times because there are n minus 1 black lines, right? I'm adding my purple line is the end line that I'm adding, one more line. So the black ones are n minus 1, so there are n minus 1 intersection points. So I enter n minus 1 new regions that are split in two, but of course I started from a region that I also split in two. That's why in total I split it. So we see that Rn is, well, the number of regions that were existing, and of those I split n in two. That means I added another n of them. I hope that is clear, that gives me the same formula, right? So let's think about it perhaps one more time. What does this say? Okay, this is the old number of regions. Now, n of those you're going to split in, you're going to double up. So n of those sit in here, and then another n you have to add, okay? You could perhaps, if you want to say it slightly differently, you could say, okay, I'm going to count each time I enter a new region, each time I cut a region, I'm going to look at, I'm going to consider the new region, the region below my line. So in this case, there were the lines that I called prime. So this one new one, okay, so this is one new one, that's a second, third, and a fourth new one. So that's n new ones, another way of thinking of that. Okay, so that's the relation. And we have also the initial condition already, right? Yes, that's the initial condition. So now B asks you to solve this iteratively. We will find other ways of solving this in the next section, but let's do this now iteratively. What does this mean? Well, you start working as a program. So you could write a very simple program that calculates this for you, right? And it's a good exercise, and I might even ask you to do that, right? In pseudocode, what would it be? So I'm not going to write the whole thing. So if n is 1, return 2, right? That would be, because that's the initial condition. Else, what do you do then? Else, return r, let's call r the function, rn minus 1 plus n, right? That's this expression. Okay, this would be a recursive algorithm that calculates this number. And if you would work out what this algorithm does, that's what we're doing here. Well, it says, okay, I take, this is my starting point. Now I apply my recursion on Rn minus 1. So what happens here? Well, by the recursion says that if n is your index, then you go one index less. So this would be Rn minus 2 plus how much? Well, also the n is gone down by 1, right? Okay, so this would be Rn minus 2 plus n minus 1 plus n. Okay, and now r minus 2 is split into r minus 3 plus n minus 2. Okay, so just you have to see what you might say. What is that? Why is this changing? Well, it also depends on n, right? So this number is one less than the original index, and this is the original index. So for instance, at this stage, if I'm going to apply this, what happens? Well, I'm going to subtract one from this index and then add the same amount. That's the new amount I'm adding. Of course, I should keep whatever I had, right? These two keep. Okay, and I keep doing this. How far? Well, I'm going to go all the way until R1. And now is the question: what else is there? What are these numbers? Well, if you just look at this, you see that, this is the one next, the following number of this one, and then so we always. This is the index, and then this number, how do you get this number? By adding 1 to this index. And then this number is by adding another n to the index. Notice again that I kind of kept it this way, and therefore I'm not adding this up yet, because that way I see the pattern. The pattern now is, okay, so as I said, this index is, what follows is the next number. Well, so this is 1, so the following number is 2, right? And then it increases all the way and it goes up to n. Okay, so that's what it is. Now what is R1? R1 is 2. So 2 plus 2 plus 3 plus n. So what is this? Well, we can calculate this thing. We have a calculation for this, a formula for this number. And what's the difference? Well, that's one. It's really this one, right? We split these two in 1 and 1. Then this one, we know that is n times n plus 1 over 2. Again, go look up the formulas that we had, table in the, I forget now, in chapter 3 or something like that. or otherwise prove it by induction. Again, you can prove this easily by induction that this is the correct formula. So the correct formula therefore is the number of limes that we get is given by this. And let's check it. We did it with 4, and we should get how many? We had 11, right? So, right. I actually never wrote down what R4 is. R3 was 7, so R3 was 7, and so R4 was 11. Okay, let's see whether this fits. So R4 is 4 times 4 plus 1 divided by 2 plus 1. That is 20 divided to 10 plus 1, that's 11. That's exactly the number that we predicted. Okay? And then number 27. Number 27, okay. What we're doing is we have a, let's say, a path that we want to tile, and we can use 3 tiles. The book uses gray, red, and green, but that's kind of annoying because they have the same initials. So I'm going to do red, blue, and green. Okay, the colors obviously don't matter. And there is only one requirement that we have. The requirement is, so this is 27, yeah, 27A, let me call it that. If the tiles are green and no 2 red next to each other. Okay? So that's the only restriction. Okay. So how do you solve? So in other words, we have n tiles here. These are n tiles. And we're going to build this, again, thinking of what if I know with how many I can do with less than n. And now I'm going to build n tile. And what you do, of course, is add 1 tile. Now, what are the possibilities? And why is it different? Well, I can add a red, a blue, or a green tile. Now, blue and green and somehow are the same. So I'm going to treat them the same. So the first thing I'm going to do is, okay, I'm saying these are n tiles. Okay, so these are n tiles here. And I'm going to add a red or a blue. So here comes, blue or green. Blue or green. Because it doesn't matter what I take here, it will always be a valid paving. Why? Because I will never have 2 consecutive reds. If my previous tile, if this tile was red, the only thing I cannot do is put a red here. But I can put blue and green there. So nothing is, whenever I put the blue and green at the end, I still have a valid pavement. Okay? So how many is this here? So let me do this in green. No, you're using green here, right? So this part here, of course, that is n minus 1, right? So what's the other alternative is that I end in a red tile. Okay. Let's look. So here now I put a red tile here. But for this to be a valid tiling, what's the only thing that cannot be? This guy cannot be red. So if I want to make something that ends in a red tile, I must make sure that the penultimate tile is either blue or green. So my options are blue or green here. Okay, and then everything else, this could be the remaining part, the initial part could be whatever it wants to be. As long as it's a valid tile pavement, then adding these 2 tiles makes it valid again. Okay, let's count now. Now starts with the counting. So this is n minus 2, right? So the number. How many of these are there? Well, so that an, did I say what? Let's call it an. So n is the number of such tiles, valid tiles. Okay. Well, in this case, what do we have? Well, we have here, we know that an minus 1 choices. And how many choices do we have here? Well, blue or green, so 2. So we get 2 times an minus 1. You could have taken the blue. You could have taken, instead of 2 cases, 3 cases. You say the first case is that the last time is a blue, the last tile is a green, and the last tile is a red. Okay, but I'm just combining these 2 cases here. Now, what is this one here? Well, okay, so I know how many there are here. That is an minus 2. That's possibilities. How many possibilities for this one? 2, right? Because blue or green. How many possibilities for one? Well, only 1. Okay. So again, this is the number I get. Are there any, so it's the sum rule, I can add them, but I have to always think, do I double count something? No, because the way I constructed it, right? So the formula is an is 2an minus 1 plus 2an minus 2. And then what are the initial conditions? Yeah, right, we didn't look at that. We know that because we go into back 2. So we will talk about this in the next section more more in detail, but it is how much we go back that is the number of initial conditions we go. We go back 2 here, 1 and 2. So we need 2 initial conditions, so we need A1 and A2. So what are the valid tilings for A1? Well, blue, green, red. So there are going to be 3, right? So A1 is 3. What are the valid tilings if I have 2? Well, now let's see. What are the ones? Blue, 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 green, blue, red, green, blue, green, 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 red, and then red, blue, red, green, but not red, red. So we could have done this a bit quicker, say, well, in total there are 2 to the, so how much is this here? We have 8, right? We have 8 of them. We could have said, okay, each tile can have 3 colors, so there are 3 times 3 different pavements of length 2, but one of them is invalid, so that's how we could have gotten to this 8 as well. Okay, that's another way of that we could have reasoned. I'm not saying that, by the way, the way that I got to this recurrence relation is not necessarily the only way. There could be other ways of getting there. So, okay, we see now that A2 is 8. Okay. And you see it's kind of a little bit like Fibonacci, although now we have these factors, these constants too there. But okay, that's not really what this is about yet. How many ways are there to lay out a path of 7 tiles as is described in part A? Yeah, so to do that, we really have to work it out, right? So we see that, let's see, it's a little bit of calculation. A7, that is 2 times A6 plus 2 times A5. So we have to calculate A6. That is 2 times A5 plus 2 times A4. So what I'm doing now is, why don't you plug it in? Because I'm not trying to get a formula. Because if I try to get a formula, like in this case here, what I had to do is start from a general n. Now I'm writing a particular n, and so on. I don't need to write as a formula. I'm just calculating these things. And I see the thing that I have to calculate, I have to go back quite a lot. Okay, and then A4 is 2 times A3 plus 2 times A2. And then A3 is 2 times A2 plus 2 times A1. Now, luckily, those I know, because remember A1, so A1 is 3, A2 is 8. So what is A3 now? Well, A3 is 16 plus 6, that's 22. So what is A4? That is 2 times 22, that's 44, plus 2 times 8, that's 16, that is 60. Okay, I'm running out of space, so I'm going to put A5 here. A5 is going to be 2 times 60, that's 120, plus 2 times A3 plus 44, that's 164. What is this then? Well, A6, that is 2 times A5, that is 328, plus 2 times 60, 120, that is 448. And we are almost there. What is A7? I'm going to write it here. It's 2 times 448. That is 9898. No, that's not good. 896, right? Plus 2 times the previous number, that is 328. So this, if I didn't make a mistake, it's 4, 1, 11, 2, 1, 11, 12. 1224. Now I have to double check this because I might have made a mistake here. Let's see. Remember, there are the solutions in the back of the book, right? And this is 20. What number was this? 27. 27. 120. Yeah, I got it right. Okay. So there were the two special problems, but I also said an optional problem was number 26 because it's an odd number, so I prefer to do it an even number, so you won't see the resolution. So number 26 was you have a checkerboard of this size. So okay, so there are n tiles here and 2 tiles this way, and you could put domino pieces on there. Okay, so the domino piece is a piece that consists of 2 tiles put together. Now, some domino pieces have different numbers on it, but we don't consider that. The question was not asked, didn't carefully stated. So for us, a domino piece is just a piece consisting of 2 tiles, and they are indistinguishable. So when I take this one or I turn it around, it's considered all the same. Okay, so we want to calculate. So let's call an the number of coverings, the number of coverings. And of course, when we start covering, we mean no tile can lie on top of another one, right? So it's a nice, we have tiled this properly. Well, let's start again with the general case. Well, again, there are 2 cases, namely, what can happen in the end? Well, in the end, either I put my tile this way, okay, that's a valid position for that tile. And what is left then? Well, let's see. We have how many are left here? N minus 1. And so these are all good tiling. Oh, sorry, this is supposed to be in this color. All good tilings. Okay. What's the second option? Well, so here we had a vertical, but we could also try to lie a horizontal one, right? But of course, if I put a horizontal one, let's think about this. So I put a horizontal one here. I have no choice. I have to put a horizontal one here too. Right? There's really no choice. There's no other way to cover those 2. So what is left here are now n minus 2 tiles. Okay. Keep doing this. Okay. So what is let's calculate the numbers now. So how many do we have here? Well, the green ones is the number of coverings that where we have n minus 2 by n minus 1, and that is given by the number a n minus 1. So this is the number of choices here. How many choices do I have here? Only 1 choice. So that's why nothing happens here. Okay. What's the number here? Well, I have and the green part is a tiling is a board of n minus 2 by n minus 2. So I know that there are n minus 2 different coverings. What about how many choices do I have here? Well, really 1 choice. This is the only option you have. If you put both there, you say, yeah, but it's 2 tiles. No, it's 1 choice. Whatever remember, all domino tiles are the same, right? So whether we put interchanging these 2 does not give me anything new. Okay, so that's the and so what is now the total? Well, again, the sum rule. So an is an minus 1 plus an minus 2. Again, there are no doubles here, doubly counted. So what are the initial conditions? So initial conditions. Well, if we have a1, let's see, what is this? That's a board of this size. How many ways can you tile it? Only 1, right? Namely this way. That's the only tile. What is a2? Well, now we have a board of this size. How many ways can we tile it? Well, I hope you see there are 2 tilings, right? They could do it this way, or we could put the bottom flat. So this would be 2, okay? And actually, so if you see, this is again the Fibonacci relation, and these are the values for the Fib. No, this is not the values for the Fibonacci. I'm sorry, that would be a 1 then. A2. Anyway, it's also a Fibonacci-like thing, and we will soon we will see how to solve these. So I'm not going to give you a formula. I think what 26 asks this for specific examples, but those are really 2 times 17. That's a lot of calculation. I don't want to do that, so I'm going to just stop here.